I'm Lily.
I'm Paige.
We did our presentation on how many licks does it take to get to the center of a Should we just okay, so it's supposed to be the commercial. No,
Start all over again.
No, because we have the access.
Tommy, you should stop.
Not really, because I don't want to.
It's no, it just
Tommy,
so that's
you should stop.
was supposed to be the commercial. I don't know if you guys have probably seen it, but the how many licks does it take to get to the center of a Tootsie Pop? It's basically this guy, this little boy going around asking different animals how many licks it takes to get to the center of a Tootsie Pop. And then he finally asks the owl and he just bites it after 3 bites. And then, so we decided to figure out how to do it using calculus. Okay, so we originally weren't going to do it on this. We were going to do it on the how much wood could a woodchuck chuck, a woodchuck could chuck wood saying that would. And we're like, okay, so we did some research and figured out that a woodchuck is actually a groundhog. And the word's derived from like a Native American term, woodchuck, and it's just used for like nursery rhymes and stuff for like alliteration. It's not really anything. And so then we like changed our topic, but we still wanted to do something kind of just fun and like a rhyme. So then we're like, oh, let's do that. How many licks does it take to get to the center of a Tootsie Pop? And so now that we know calculus, we thought we could do it the math way. Okay, so we have some for you.
The history of the Tootsie Pop, it was invented by Louis Graham in 1931. He was just about to go to a company meeting when his daughter asked him to take a lick of her lollipop while he was eating a Tootsie Roll, and he liked the taste of the combination, so he brought that idea to his company meeting, and later they were selling in stores the Tootsie Roll, Tootsie Pop. The first flavor was chocolate, and it was ideal that it came out in 1931 because it was just around the time of the Great Depression, and so it was a cheap snack, as well as it came out during the period of World War II. So it was a good snack for soldiers, and it was able to withstand many weather conditions.
And then the history of the slogan, the commercial first aired in 1970, and that's when the slogan, how many licks does it take to get to the center of the Tootsie Pop, was first featured. Oh, another little fun fact is, I don't know if you guys have ever heard anything about this little guy being on the wrapper of your Tootsie Pop. It was always just, or there was a rumor that it was, you would get a prize or something if you had one on your wrapper, but it was just a myth and basically nothing happened. Okay, so how we measured, we started off by, if you look at your sucker, one of us would measure like the ridge part, and then also like the circular part, like horizontally like this. But then, and we measured in centimeters, but then we figured out that that wasn't very accurate because as you lick it, the ridge goes down, so it's hard to measure the ridge and the circular and keep it accurate. And so then we measured just right through the ridge, and we did that in millimeters, and we figured out that that was more accurate because it stays more consistent. And so here's our data from that. So every 30 seconds we would measure, and so that's from the start without licking, and then this is the end. It took us 26 seconds.
So as you can see, we ended here at 750 seconds, and that is 26 different 30-second intervals of sucking on the sucker. And so to find how many licks, we had to first see how many licks we could take in the 30-second interval. We found that we were able to take 22 licks in the 30-second interval, so of 26, we did 26 times 22 to find that it would take us 525 licks to get to the center.
And then just for fun, we all actually did the normal way, and we just licked them. And we've got different answers, like when we printed out these little certificates saying how we did it to Zero website. But, so we all got different answers because everybody's different. So I got 527, and Lily I think got 530 or something, but they're all pretty close. It's just okay. And then We also wanted to find the volume of the suckers, so we plugged each radius into the volume of a sphere equation and found all the different volumes at each time interval, and then from that we were able to find the rate of change.
Okay, so our first step was that we wanted to find the rate of change of the radius after each time interval of sucking on the sucker. We wanted to see how fast the radius was shrinking, and related to that we wanted to see how fast the whole volume was shrinking. And so what we first saw was, after we took all the measurements, we saw that the sucker was decreasing at pretty much a constant rate. It was really close to just decreasing the same amount each time, no matter how big the sucker was or how small it was getting more towards the end. So to find dRdt, the rate at which the sucker was decreasing over time, we used the data from this table. We plugged all those into our calculator to find the line of best fit, which we found was negative 0.01168x plus 15.108. So then we knew from that that this number here is dRdt. So with that information, we plugged that into the equation for dVdt. And first of all, to find dVdt, we just took the derivative of the volume equation. And so we plugged in dRdt, but then to know which radius to use, since we had 26 different radiuses, we decided to find the instantaneous rate using the first coordinate from the radius graph. So using the starting radius before we did any sucking, and then the ending radius from when we reached the center. So we used those 2 points to plug into the equation. And so we put that here. This is dVdt for the last radius. This is dVd for the first radius. And then we put that over, divided by the 2 radiuses to find that the decreasing rate was negative 3.0635 millimeters cubed per 30 seconds. So then to find the rate at which it was decreasing per second, we just divide that by 30 to find that the rate of the change of the volume was negative 0.102 millimeters cubed per second. And these are the 2 graphs. So this is the graph of the rate of change of the radius over time, and this is the graph of the rate of change of volume over time. So you can see how they're related, that as the radius shrinks, so would the volume.
So we also wanted to find the rate of change of the surface area and the circumference. So we took the equations for both of those and then took the derivative and plugged the radius into that to find the rate of change of the surface area, which is negative 0.14, and then the rate of change of the circumference, which is about negative 0.07.
Okay, so some history on related rates. There was a man named Reverend William Ritchie, and he was a professor at this university in London. He was the professor of natural philosophy, and he wrote a book with the guy who was the professor before him, named J. Sylvester. And so they wrote this book, Principles of the Differential and Analytical Calculus, and they used Newton's ideas in calculus, and they just wanted to simplify it and see the rate of change of something of the size of something over time. And so how they did this, they wanted to do it simply so that they could teach it and just keep it easy. And so, I'll go back. So they introduced limits and stuff, and then they used an expanding square and a function, and just saw how they related, and then when one increased, so did the other.
So how related rates are applied. Related rates are basically how the rate at which one quantity changes in relation to another quantity. And so for this, it was the relation of how the rate at which the volume and radius changed in relation to the time of the sucking intervals. And then, so other applications of related rates could be basically anything where 2 things are moving in relation to each other. So if 2 people are moving away from each other and you have both of their rates. You can find the rate at which their distance increases or the rate at which a balloon is being filled. You can find the rate at which the volume is changing. That's it.